Hello! In this video, we are going to prove the following theorem. Let I be an interval, let f be a function from I to R, and let C be an element of I. Then f is differentiable at C, if and only if there exists a function phi from I to R that is continuous at C and satisfies f of x minus f of C equals phi of x times x minus c for all x in I. In this case, phi of c is equal to f prime of c. Now, when we say, in this case, phi of c equals f prime of c, what that means is the following. If we're given f is differentiable at c, then we can show that there exists a function phi from I to R that satisfies these properties, and it also satisfies the property that when we send c into the function phi, it ends up being the derivative of f at c. Conversely, if we're given that there exists a function phi from I to R that satisfies these properties, we can show that f is differentiable at c, and the value for the derivative of f at c is precisely phi of c. So this is often called Caratheodory's theorem. Now, before we get into proving it, let's first remind ourselves of some things. By definition, to say f is differentiable at c means the following. To say that f is differentiable at c means that the limit as x approaches c of this function, where the domain is all x in I set minus c, exists. So it means that this limit exists. Now, when this limit exists, we call this limit the derivative of f at c, and we denote it by f prime of c, like that. Now, by definition of the limit of a function, to say that this limit is equal to f prime of c means the following. By the epsilon delta definition of a limit, to say that the limit of this function is equal to f prime of c means this. So we have for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the domain of our function, if 0 is less than absolute value of x minus c is less than delta, then the absolute value of the output value of our function at x minus f prime of c is less than epsilon. Right, so this is what it means for f to be differentiable at c. Now, we're also going to need to know what it means for phi to be continuous at c. By definition of continuity, to say that phi is continuous at c means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the domain of our function phi, if absolute value of x minus c is less than delta, then absolute value of phi of x minus phi of c is less than epsilon. Okay, so now let's get into proving this theorem. To start with the proof, we're first going to prove the forward direction. We're going to prove if f is differentiable at c, then there exists a function phi from I to R that satisfies these properties, and phi of c is precisely equal to the derivative of f at c. So to prove the forward direction, let's suppose f is differentiable at c. From here, we want to show that there exists a function phi from I to R with these properties. And we are going to explicitly define a function phi right now. So we define phi to be a function from I to R, and given x is an element of I, if x is not equal to c, we will say phi of x is equal to f of x minus f of c over x minus c. If x is equal to c, we will say phi of x is equal to f prime of c. So we're going to show that this function phi that we've defined satisfies these properties. So let's first show that phi is continuous at c. By definition, to say that phi is continuous at c means that this statement is true. So we want to prove that this statement is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a delta greater than 0 such that this is true. Now, to figure out what we should choose delta to be, we use the fact that f is differentiable at c. So since f is differentiable at c, that means that this limit exists, and we say it's equal to f prime of c, right? We call that the value of this limit. But then, by definition of the limit of a function, that means that this statement is true. And this statement works for every positive number, so in particular it must work for the positive number epsilon that we just introduced in our proof. So taking this positive number to be the epsilon in our proof, well then there exists a delta greater than 0 such that for all x in I set minus c, if this is true, then this is true. Now remember, we're trying to prove that phi is continuous at c, which means we're trying to prove that this statement is true. And so to do that, we give ourselves an arbitrary epsilon greater than 0, right here. From here, we want to find a delta greater than 0 such that this is true. The claim is, if we take delta to be the delta that we have here, then it will work. So with this choice of delta, we're going to prove for all x and I, if this is true, then this is true. So to prove that, let's give ourselves arbitrary element x and I, and suppose absolute value of x minus c is less than delta. From here, we want to show that the absolute value of phi of x minus phi of c is less than epsilon. Now, we're going to split that up into two cases. If x is equal to c, well then clearly absolute value of phi of x minus phi of c is less than epsilon. Because we would get phi of x minus phi of c equals phi of c minus phi of c, which is equal to 0. Absolute value of 0 is 0, which is less than epsilon. So this covers the case x is equal to c. Now let's consider the case x is not equal to c. If x is not equal to c, what is phi of x minus phi of c going to be in this case? Well, since x is an element of I, but not equal to c, by definition of phi, that means phi of x is equal to f of x minus f of c over x minus c. But then we are subtracting phi of c. By definition of phi, phi of c is equal to f prime of c. So that's what we get. But we should have that this guy is less than epsilon. And we do. Since we know x is an element of I but not equal to c, that means x is an element of I set minus c. Further, since x is not equal to c, we have absolute value of x minus c is greater than 0. So this inequality is satisfied as well. So since x satisfies both these conditions, we can conclude that this inequality is true. So this guy is indeed less than epsilon. So that gives us absolute value of 5x minus phi of c is less than epsilon. So no matter what, whether we have x equal to c or x not equal to c, we have that absolute value of 5x minus phi of c is less than epsilon. So we've shown that this is true. And therefore we have proven this statement, which means we have proven that phi is continuous at c. So we've shown that phi is continuous at c. Now we want to show that phi satisfies this property. So we're trying to prove a statement about all x in I. So let's give ourselves an arbitrary x in I. From here, we want to show that this equality is satisfied. Now, to show that this equality is true, we're going to split this up into two cases. Either x is equal to c or x is not equal to c. If x is equal to c, well then the left-hand side becomes f of c minus f of c, which is equal to 0. And the right-hand side becomes phi of c times c minus c, which is also equal to 0. So both of these guys are equal to 0, and so they're equal. So this covers the case x is equal to c. Now let's consider the case x is not equal to c. if x is not equal to c, well, we have x is an element of I, but not equal to c. So when we send x into the function phi of x, by definition, is equal to f of x minus f of c over x minus c. So then we just multiply x minus c to the other side. We get f of x minus f of c is equal to phi of x times x minus c. And so that's it. So no matter what, given any element x and I, whether we have x equal to c or x not equal to c, we see that this equality is true. So we have shown that this is true. Next, we know phi of c is the derivative of f at c. That comes directly from the definition of phi itself. Just send c into the function. Since c is equal to c, you get phi of c is equal to f prime of c. So we're done. We see if f is differentiable at c, then there exists a function phi from I to r that satisfies these properties. That proves the forward. Now we're going to prove the converse. Now to prove the converse, we're trying to prove if there exists a function phi from I to r that is continuous at c and satisfies this equality for all x and I, then f is differentiable at c. And moreover, the derivative of f at c is precisely phi evaluated at c. Right? That's really what we're trying to prove in the converse. So, to prove the converse, we will suppose that there is a function phi from I to r that is continuous at c and satisfies this equality for all x and I. From here, we want to show that f is differentiable at c. By definition, that means we want to show that this limit exists. So what we're going to do is we are going to show that this limit exists, and in fact, the limit of this is precisely equal to phi of c. If we can show that, that means the derivative of f at c is phi of c. So we will have f prime of c equal to phi of c. And so we'll be done. So to prove that this limit is equal to phi of c, that means we want to prove this statement, but replacing f prime of c with phi of c. So this is the statement we want to prove. So, since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a delta greater than 0 such that this is true. Now, to figure out what we should choose delta to be, we're going to use the fact that phi is continuous at c. Since we know phi is continuous at c, that means we know that this statement is true. This statement works for every positive number. So in particular, it must work for the positive number epsilon that we have here. So taking this positive number to be the epsilon in our proof, it follows that there exists a delta greater than 0 such that for all x and I, if absolute value of x minus c is less than delta, then absolute value of phi of x minus phi of c is less than epsilon. So, we're trying to prove this statement, right? And to do that, we have given ourselves an arbitrary epsilon greater than 0 right here, and we're trying to find a delta greater than 0 such that this is true. Well, all we're going to do is we're going to take delta to be the delta that we have here. So with that choice of delta, we will prove that this statement is true. So to prove this statement, let's give ourselves an arbitrary x in I set minus c, and suppose 0 is less than absolute value of x minus c, less than delta. From here, we want to show that this inequality is true. So let's write out the left-hand side. Now, since x is an element of I, we know that this equality holds for all elements of I. So in particular, it must hold for x. So we know that this equality is true. But since x is not equal to c, we can divide x minus c to the other side. And we get phi of x is equal to f of x minus f of c over x minus c. So we can replace this guy with just phi of x. So this just becomes absolute value of 5x minus 5c. But then, since x is an element of I, and absolute value of x minus c is less than delta, that tells us that x satisfies these two conditions. So we can conclude absolute value of 5x minus 5c is less than epsilon. So that's it. What this shows here is that this guy is less than epsilon, which is exactly what we wanted. So we have proven that this statement is true, which proves that this limit exists and it's equal to 5c. So we've proven that this limit exists, which means, by definition, that f is differentiable at c. So, f is differentiable at c. The value of this limit is precisely the derivative of f at c. So in other words, we have shown that f prime of c is 5c. And that's it. That proves the converse. And so this completes the proof. And so yeah, that's pretty much it for this video.